Hi, I'm Kevin Bond. Welcome to my talk, Delphi and Functional Programming using Anonymous Methods. I'll begin with a little background and then I will go on to explain some concepts: function, function type, function application, partial function application, function composition, lambda calculus, and anonymous functions, first-class objects, higher-order functions, map, reduce, filter, and closure, via some demonstrations in Haskell and also in Delphi. I will look under the hood at how Delphi implements anonymous methods using the RTTI, in other words, engaging in reflective programming. I'm going to demonstrate how anonymous functions are very effective in parallel programming in enabling the execution to be sped up enormously compared with a single threaded application. And I'm going to demonstrate callbacks in asynchronous programming in Delphi and Cortex Pascal. Okay, the Delphi and Cortex Pascal programs covered in this talk will be anonymous functions and function application. And if there's time, I will look at event handling. Oh dear, I spelt anonymous method incorrectly, but never mind. It's just instinctive to add the E to mouse. Okay, where does it all start? This is the background. I went to a rebooting computing conference in 2009. It was held in Mountain View, California, addressing the issue, the falling numbers being recruited to computer science courses in higher education, and also the dropout rate from HE courses in computer science. And it really was attributed to the lack of opportunities for self-directed learning in programming computer science outside of the school environment, and also the school curricula, which had this emphasis on IT, essentially teaching not much more than Microsoft Office programs, and so there was a need to think about how could we tackle this. I talked to Professor Quinton Cutts while I was in California. He's a professor in computer science education at Glasgow University in Scotland, and I don't know how the conversation got on to functional programming, but it did. And I thought, actually, if we get a chance to rejig our syllabus, then I would like to include some functional programming, because other conversations I've had at other conferences were suggesting that this would be a good thing, and it would also give students an experience of what type of computing they would engage with when they went on to higher education on computer science degree courses. So I did manage to incorporate this into the A-level computer science syllabus, and there is a section called Fundamentals of Functional Programming Paradigm, and we'll just have a quick look at that content. I won't spend too much time on it, but basically there were several strands to the strategy that evolved not only from this conference but also from what was taking place in the UK. I've been contacted by Professor Keith Mander, who was head of the computer science department at York University back in the early 2000s, worried about the recruitment crisis, and he wanted to pick my brains. Lots of other people were engaged in this, so the feeling was that computer science courses had healthy numbers in the days when there was a BBC microcomputer, the ZX Spectrum and ZX81, when students had a chance for self-directed learning outside of school, because they had a very cheap computer system that they could engage with, and that had disappeared. So the Raspberry Pi single board computer project was born out of this. The computer science the Community at School organisation that began in the UK in, I don't know, 2006, something like that, which I was a founder member, brought about a change in the national curriculum by lobbying the government. So we have more computer science programming in our compulsory curriculum with the 5 to 16 curriculum. But there are also lots of other initiatives taking place. Universities, other organisations were engaging in trying to create opportunities for students to engage in programming activities, computer science activities. Professor Tim Bell, University of Canterbury, New Zealand, brought out CS Unplugged, sponsored by Google, which was Computer Science Unplugged from the Computer. Professor Paul Curzon, Queen Mary University, London, has been funding and delivering a magazine to schools called CS for Fun, a sort of a very engaging website to try and get engagement. He ran a series of events for schools over 3 or 4 years with a colleague, which is basically basing teaching computer science on magic, which was very engaging. So lots of initiatives. So finally we got what we wanted. So I added to our syllabus fundamentals of functional programming. So the function type. Know that a function f has a function type where the type is A maps to B. A is the argument type, B is the result type, A is called the domain, and B is called the code domain. So loosely speaking, a function is a rule that for each element in some set A of inputs decides an output chosen from set B without necessarily using every member of B, for example. And then the idea that functions can be first-class citizens or objects, so they can appear in expressions, be assigned to variable, be assigned as arguments, be returned in function calls. That's quite important because we can call a function which actually returns a function. So we have an opportunity to create a partial application of a function, which is quite a powerful idea. So the idea that when you apply a function, we have a function and its application to an argument is called function application. For example, also functions have type, so we might have a function which combines 2 inputs in a combination known as Cartesian product set, or Cartesian product rather, and it returns an integer. So the idea of specifying the type of the input and type of the output in this particular form has its origins in lambda calculus, which I will cover as well. Partial function application I've mentioned, where you have a 2 input function which returns an integer, but if you only supply 1 integer input, what is actually returned is a partial function which maps an integer to an integer. So we can drop the brackets. So this is rather strange at first when you think that, but you just write integer forward arrow integer forward integer for the total function. Composition of functions, which basically means the output of a function becomes the input to another function, which is quite a powerful idea. So if we had a function f of x equals x plus 2, and we supplied the output of that to a function which basically cubes its input, then we'd end up with a composition which was x plus 2 cubed. So writing functional programs, centers, we call them centers, the schools, colleges or whatever, have a choice from functional programming language. Haskell was the one most centers chose, but they could also do their functional programming in any one of these multi-paradigm languages, Python through to VB.NET or Delphi and Delphi XE version onwards, when Delphi anonymous functions were introduced into Delphi 2009. We have higher order functions. A function is higher order if it takes a function as an argument or returns a function as a result, or does both. So we have map, filter, reduce, or fold. And list processing as well. So that represents the empty list. This is a list in Haskell, and I will demonstrate some Haskell programs shortly. Okay, so back to the presentation. So coming back to the UK, I working with the lobby group competing at school organisation. We got the national curriculum change. We also managed to introduce a GCSE, which is a 14 to 16 studied course in computer science. which was a first, and then for our 16 to 18 qualification advanced level, we were able to get rid of the subject criteria which we shared with our ITA level. So we had a very specialist subject, a computer science subject criteria, which we had to meet and cover in our revised syllabus, which we did, which we have done. Okay, just mentioned I wrote a couple of books to support this course, so apologies for the unashamed plug. All roads lead to Delphi. I've been a supporter of Delphi for a very, very long time. I cut my teeth a very, very, very long time ago on Fortran and then BCPL, PDB11, BASIC, etc., etc. But I started programming in Pascal when I left industry, set up a computer science department, and started teaching A-level computer science to 16 to 18-year-olds, and a school founded in 1598 with some very, very exceptionally bright students. And I taught Pascal and then Object Pascal when it came along, and then jumped at Delphi 1.0 to do events driven programming with graphical user interfaces. But I'm trying to think of a strategy to get Delphi back into schools in a major way, and back into the hobbyist, etc., the self-directed learner. So I came across PascalABC.net a long time ago. It was developed a collaboration between Russian and German universities to produce something for schools. It's used in Russian schools and quite a few German schools. And I think this is a good way in. It's .NET based, it's event-driven, form-driven, Object Pascal, but it also supports functional programming, because it implements Link under the via .NET. So I could create a function. This is a 2-input function. Both inputs are of type integer, and the output is integer. So the style is to write first input, second input, and then the output. If you can imagine, if I put a bracket here and a bracket there, if I supplied one input, what would be returned would be a function of a single input. In other words, it would be a partial function. So then I thought, well, a long time ago in 2009, what would be a good way to introduce object-oriented programming based on Object Pascal? And I tasked a student of mine with a project. They have to do a project for their A-level, and they do it over a very long period of time. Very bright student, and I had a conversation at that rebooting. No, it wasn't. No, I can't remember now. Talked to Michael Colin, who's the creator of Greenfoot, which is very, very similar, but it's based on Java. And I floated the idea that I'd like to do something in Delphi along similar lines. He said, fine, go ahead. But he said the critical path is not this IDE, but the infrastructure surrounding it. And the key to this is a sharing environment, i.e. a website where students can upload their work to showcase it and share what they've done with other students. And I realized, yes, that is a very, very important part to this. So I was looking around for a way of converting Object Pascal programs into JavaScript, so they could run in a web browser. And I came across Cortex Pascal, which is under development, only available to backers, but version 1.1 will be out in a few months, and it will be free to education. And what I've done is I took a Delphi FMX application, which if I can, maybe I'll come back to this, but I've actually got it. Yeah, here it is. If I just bring up my mobile phone, which I created for my Samsung S8 Plus mobile phone, and so this is running on my phone. I'm just showing the phone screen, because if I were to go to something else, I mean, I could go and have a look at what else could I have a look at? I could look at my timer, So this is the right timer running. Sorry, that was an earlier run, so that's not the current timing of this recording. Okay, so I thought, okay, take this and just put it through Cortex Pascal so I can run on the web. And I'll demonstrate this later on, because it is an application of anonymous functions in a callback. And then of course, education is now getting into using generative AI. The Raspberry Pi Foundation, which has got a solid, it's on a solid financial footing now, because the Raspberry Pi was subject of an IPO recently, which raised about 160 million. So that's gone to this Raspberry Pi Foundation to support education. It was being supported by revenue from the sales of the Raspberry Pi. I think about 60 million have been sold now. And they've produced some teaching materials for generative AI. And I want to explore, or a lot of people are exploring Delphi and generative AI, but from the point of view of education, because I think that's also a way that we could get Delphi back into prominence in schools. And so I'm going to come back to this. So, and then of course I produced a book to support teachers and students and hobbyists and so on, and anybody wanting to learn Delphi, because I think very, very important that there's a readily accessible textbook if people wanted to engage with Delphi and start going and go from the basics up to some support. You can go to that link there. Actually, this was created in Cortex Pascal, and I've got 8 videos on anonymous methods. 5, 6, and 7 cover higher order functions, map, filter, and reduce. Part 8 covers closure. Okay, the functional programming paradigm. Anonymous methods originate with lambda calculus, which belongs to the functional programming paradigm. So explicitly created to support a pure functional approach to problem solving. Functional means overall style of the language is organized primarily around expressions and functions rather than statements and subroutines. So this is a declarative style of programming. The brain to code distance is shortened by being high level, so it's well above the von Neumann architecture, which is statements and subroutines orientated. So the primary unit of modularity in functional programming is the function, whereas in object-oriented programming, the primary unit of modularity is the class. So functional programming means building programs from pure side effect-free functions, but there's the conundrum, because any application worth its salt has to interact with the outside world. So you're going to end up with impure functions. But the way that it's done in functional programming is to isolate the impure functions in something called actions or monads, and then never ever allow a pure function to call an impure function, but always do it the other way around. Impure functions call pure functions. And because the impure functions are isolated, that aspect, which is the dangerous part, as it were, can be dealt with effectively. So structuring programs from function composition and using recursion instead of loops, writing pure functions so that the result of a function is fully determined once its parameters have been fixed. So if I say square 2, I should never be surprised by getting an answer which isn't 4. That's what is meant by a pure function. Side effect free functions. I haven't changed or altered any part of memory by updating a variable, because in functional programming, pure functional programming, variables are immutable because they're not variables. If you can't use an assignment statement, they don't exist except with regard to I/O in functional programming language, because you cannot say x becomes equal to x plus 1, i.e. you can't update a variable. If you want to work with a new value, you have to take a copy of that variable, do something with it, and and identify it with a I keep saying variable, they're not variables. I'll think of a better term in a minute. So you avoid side effects, doing literally nothing except evaluating the result. You impose immutability, the ability to change the value of a variable. The inability. And some functional programming languages allow lazy evaluation, which means you can deal with infinite lists. And I'll demonstrate this in Haskell, which is one of the languages which does. Haskell is a pure functional programming language. It is the standard because variations on a theme proliferated in the functional programming world until about, I can't remember, it was 1998. And it was decided to organise a conference to decide on a standard, and the standard which emerged became the Haskell programming language. Isolate those parts of the program that interact with the world and use actions or monos to enable imperative style programming in pure function. So, okay, let's get on to the meat of this talk. Lambda calculus and anonymous functions. Anonymous functions originate in the work of Alonzo Church in his invention of the lambda calculus in 1936, in which all functions are anonymous. This work ran parallel to Turing machines, which Alan Turing was working on at the time, and they are both different takes of the same thing, basically, or different takes on the same thing. Sorry, let's get going. Okay, so this is an anonymous function. Okay, the lambda symbol here means what follows is a function, and the function type is here. It says it takes one input called x, and what it does is it returns x times x. So this is a function without an identifier. So it's not bound to an identifier. In Haskell, which I'm about to demonstrate, it will be written like that. Okay, and when we want to apply that function to a specific value of x, this is called function application, we surround the anonymous function with brackets and follow it with the actual value that we want to apply this function to. Now, you could go to Replit online, and they've recently updated it. And to be honest, I'm more familiar with the installed Glasgow Haskell compiler interactive system, which is what I'm going to use for my demonstrations. So lambda expressions is as a name x or a function at or a function application are really just anonymous functions in a concise form. So a lambda calculus is a system for manipulating lambda expressions. Okay, so I want to go to this and also, oh golly, wait a minute, I think I'm going to come out of this just for the moment because I want to go into two things at once. No, I don't want that. I want this. So I don't want that, but I do want my prompt sheet. So I'm going to launch the Glasgow Haskell compiler interactive system, which I've already installed on my machine. So I just type GHCI, and now I'm in. So if I wanted to run this Haskell function application, I'll paste that in, and we get 36, which is what we expect. Now, to demonstrate partial function application, what I need, before I do that, let's make let's demonstrate a two input function. Now, if you like, I'm going to break it down into this function, which is an anonymous function with a single input y, and what it does, it calculates x plus y, but I haven't supplied x yet, so I'm going to say that this is a partial function application, because if I create a function which supplies a single x, and it returns, because what's on the right side of this arrow returns is a function where I've supplied a value for x, so all I'm left with is the need to supply a value for y. So I'm sorry it sounds a bit convoluted, but I have a couple of graphics later on to make this hopefully clearer. So I supply argument with value 1, which will be bound to this value x here, so it will go into here as 1. So all I need to do now is apply a value for y, which is the second argument. So we expect 1 to be added to 5, and we get 6. I could have actually written this a slightly different way, maybe a little bit clearer. I could have said x, y, that's 2 inputs, goes to x plus y, and then I write, to make this a functional application, I close the bracket, 1 plus 5, and we get the same result. This is slightly different because this actually returns a partial function, one that's still lacking something. Okay, so I'm going to, this is equality. So this says I could either use this or I could use this once this statement has been accepted into the system. So let's try this. Okay, so I've actually created something called add n, which, well, it's similar to this, so it requires 2 inputs. Stupid me. What I should have done is I should have said, let's make a partial function called add1, which will be add n1. Okay, good. So now I require one more argument to complete the function application. So add 1, 2 gives me 3. Okay, so that's because we have a function in which the n has been replaced by 1. So now when I supply the argument 2, 1 will be added to 2 every time. Okay, so it can get a bit more complicated if I have a 3 input function. The first argument 1 replaces x, and what is returned is this, with x being 1. The second argument replaces y, and what is returned is this, with x1 and y5. And then finally I supply 3 for z, and z is replaced, so this becomes 1 plus 5 is 6 plus 3, which is 9, which is what it is. Okay, function composition. So what have I got here? So I'm looking at this one. Yep, got my head around this. So if I do this, okay, what have we got here? We have got a single argument function which squares its input, and this is the function application because this is applied to 4, which should give us 16. So 16 now becomes the input to this function, so replaces x. So 16 has 1 added to it, so it should be, the result should be 17, which it is. There is another way of expressing this function composition, which is using this chaining method. So if we go here, okay, so I've dropped this bracket here, and so it's been replaced by this. So it's basically saying supply 4 to y first of all and calculate its square, and then what is returned is then supplied to this. So we should get the same answer. Okay, we can do a prefix operation here because we make a function called plus, which is applied. So this is function application again. Plus is dyadic, so it needs 2 operators, so we get 5. I can use this function chaining with inverse square. So here, the square root function, in a moment I'll apply it to 4 first of all. So the square root of 4 is 2, and then I'm going to apply the function 1 upon, so this should become a half, and so this function chain, this composition here, it's composing 2 functions together, is equal to inverse square root. So wherever I want this, I can replace it with inverse square root because they are one and the same thing, because this is a quality, and then I'll apply it to 4. So I've made the composition. So if I now do inverse square 4, like so, I get 1 upon 2, which is a half. Okay, I've demonstrated that already. Okay, so I'm going to import something that supports list operations because I'll need that next. So if I come over here, import. So the prompt tells me we've now got the data.list module load. So this is lazy evaluation because I've got I specify a list in square brackets, and it's an infinite list. And what I'm going to do, I'm going to take the first 5 elements of this list. So I can come over here. So one of the things about the Haskell compiler, about a lot of functional programming languages, is the order of evaluation doesn't, well, when I say it doesn't matter, there's no static checking. So you can have something where it's not fully defined, and the definition comes later, and that list of 1 to 50. Okay, immutability. So what I'm going to do is say I have a list 1, 2, 3, but that's equal to B. So wherever I have this 1, 2, 3, I could also replace it by B, or wherever I have B, I could replace it by 1, 2, 3. But what I cannot do is I cannot alter B because it's immutable. So if I set that up, I just show you that it's there. Okay, B, and I can reverse this because reverse is an operation that's in the library data.list, so I can reverse B. So this returns a reverse list, but it hasn't altered B. Okay, we come to the first Delphi project, a polynomial sum, which uses an anonymous function. So how do we create an anonymous function type? Well, we do it with the keyword reference and the keyword to, and then the keyword function, and then we say what is the label or identifier for the input and what is its type, what is the type of the result returned. Okay, and basically I have a function sum here which has 2 arguments. So we're going to sum to some value of n, and we're going, sorry, my mouse is playing up, not my mouth but my mouse. My mouth is possibly also playing up as well, but never mind. So f is the anonymous function which we're actually supplying here. So you can see it's got no identifier, but its signature is the same as this, and it returns a result x. So yeah, this is a trivial example, but okay, we're supplying the number 3, so we're hoping to sum to 3. So what does sum do? Well, sum initializes its own result to 0.0, and then it iterates. So what it does, it will call this anonymous function first of all with 1, so 1 is returned, and then it will be added to the result, which is 0, which is 1, and then this will iterate round, and we'll end up with the sum 1, 2, 1, 2, 3. So just to point out that this function type is not a function pointer. You may have encountered function pointers which would be defined a la so, and a variable of that type would be defined or declared as shown. Neither is it a function reference for a function contained in an object, i.e. an instance of a class, because that would look like this. It is actually an interface type definition. Now, I can't think of Barry. I can't think of his last name for the moment. Created anonymous functions in Delphi back in, they were first introduced into Delphi 2009. Functional programming languages need a garbage collector because they make heavy use of the heap. We don't in Delphi need to do that if we actually implement an anonymous function using an interface type, because interface types are very good. They tidy up after themselves, so they release the space which they claim on the heap. So a brilliant idea, okay, to use the interface type. So what does the compiler do? It takes this t-polynomial function reference, which is actually under the hood an interface definition, and I'll explain in more detail later, and it creates a class that implements this interface, and then it goes on to create an object of this class containing the function f. Now it's at this point that this object stores a function pointer to f, but it's all hidden under the hood. So I'm going to try the polynomial sum project. You could try it in Delphi 10, 11 or 12. Because I've got everything set up on this machine in Delphi, I've got lots of libraries added to it, and I have another machine for Delphi 12, but it's just lots of other things are there, like all the Haskell stuff. So what I'm going to do is I am going to switch now to Delphi. If I remember to set it up this morning. Come on, why has it got stuck? I'm actually going to stop for them. Right, here we are in the polynomial sum project. I've actually added, in addition to this sum to n, I've got sum to 100, where the anonymous function is returning cos of the argument x, and then I've got another anonymous function which where the result is 1 upon 2 to the power of x, and then I've got another one which will range, this one was from 1 to 10, this is from 1 to 15, this is from 1 to 40, this is from 1 to 50. So if I compile and run, so let's make sure this is big enough. So font, let's make it 24. So you can see here that the sum from 1 to 3 using this anonymous function is 6. Summing from 1 to 100, cos 1 plus cos 2 plus cos 3, etc. is minus 0.53, and then when I try and sum the power series, a half plus a quarter plus an eighth, and I go from 1 to 10, 1 to 15, 1 to 40, and I think the last one was 1 to 50. So you can see we get closer and closer to 1. Okay, so returning to the PowerPoint. Okay, the next one is a Delphi example of partial function application. So here is our function type. I could have used the generic tfunc integer to integer because that's available in Delphi, but I'll just stick with this for the moment. So it's integer to integer. So what I have is this this function will actually return this function. So you'll notice that function f of argument x returns this function type. So this has is this basically, because it's the signatures match. Okay, so I call this function value 2, so I'm calling it with x equal to 2, and what we get back is this function in which x is now bound to the value 2, and this is the I didn't mention in the previous slide, but this is an example of closure, because when this call returns, it will have disappeared off the stack, but the value given to x is retained, it's been captured, and this is an example of closure because it's now bound to the function which is returned. So if I then supply a value for y, 6, then we evaluate x plus y fully. So let's so I'm just going to need to get something that's on my screen which you can't see, which is in the way. So in computer science, a closure is right, Gordon Bennett. In computer science, a closure is a first-class function with free variables that are bound in the lexical environment. A closure is a first class with free variables that are bound in the... Okay, if we look at this function here, y is bound to this function. So this y here is bound in here. But when you look inside this function, you say, where the hell does x come from? So that is free. When you, if you're only living inside this function here, you've no idea where x comes from. It comes from outside. So x is a free variable, while y is a bound variable. So a closure captures variables from its surrounding scope and is able to use these variables at execution time, even though these variables are no longer in scope. Because if you, when a function is called, somewhere in the first 1, 2, 3, 4 stack cells, those the actual parameters are supplied on the stack in those first few cells or whatever. So it's out of line programming basically. Okay. So it's an out-of-line function, and it's able to use these variables to execute, even if these variables are no longer in scope. Hey, closures preserve the outer scope inside an inner scope. Closures only make a function impure if you modify the closed over variable. So I can imagine an application where you want to make a counter which you can increment. Let's call it increment counter, and you actually capture a free variable when you're setting it up. So you make a call which returns this increment counter. So it's initialized, let's say, to 0. And then every time you call increment counter, you increment it by 1, let's say. So you can specify in the argument to increment by how much you want to increment. And then you are actually modifying a variable. So you're going to its memory location and you're altering it. And that is what happens in an assignment when you say x becomes equal to x plus 1, let's say. And that is not then a pure function. Every time you call increment counters, you get the same value back, which you wouldn't do, because the whole purpose of a function like a random function, you want a random number, so you'd be very disappointed if you got the same random back every time. Okay, so let's quickly go and have a look at this example. So let's escape from there and let's go to this. So I want to close this. And I want to go on to oh golly, what did I call it? Delphi Add 2 project. I thought it was Delphi Add 2 project. So let's go to Delphi Add 2 project. Make sure it's selected, and let's show it's so very simple program. Oh, this time I'm deciding that the y variable will be 60. So f2 returns a partial function, which I then which is bound with x bound to 2. So it will create 62. So if I run it, not a complicated example, and so it's 62. Okay, right. From little acorns, big oak trees grow. So we're starting in a very, very simple way. So let's, from the current slide. Yes, sorry, I can say at this point, as I said, this is modeled as an interface, and under the hood, a class is created from this interface, and then an object is created based on that class, and this is the object. And so in order to implement closure, that class has a field labeled x, and now in the object here it is, and it's captured the value 2. Ffunc is where the function pointer goes, pointed to the code for this. Okay, solid principles of object-oriented design. What have these got to do with anonymous methods? Okay, you'll see in a moment. Single responsibility principle, open-close principle, Liskov substitution principle, interface segregation principle, dependency inversion. So it's the single responsibility principle. Every class, module, or function in the program should have one responsibility or purpose in the program, or every class should only have one reason to change. The interface segregation principle, the interface of a program, should be split in a way that the user client would only have access to the necessary methods related to their needs. So combining these two principles in extremis, then every interface should have only one method. Well, hang on a minute. An interface with only one method is just a function type. So anonymous methods implement the single responsibility, or obey the single responsibility principle and the interface segregation principle. Okay. Right. Wow. So so this is the square project where this gets a little bit complicated. So if we have a function type, which is a reference to a function, so this is how we introduce our anonymous function. Compiler generates an interface T function of integer with a single method invoke with the same signature as this function. An interface is a class with no implementation. So what we end up with is sorry, this should be I. This should be I, function of integer. Sorry, got that wrong. Interface function invoke. So this is the interface with a single method. So if we have a variable called square, and we assign to it an anonymous function, this one here, we can engage in function application by doing square 6. Okay, right. So under the hood, yeah, I think I should have put I here because it's confused. That should have been I. So I said that under the hood, Delphi will create a class based on the interface. So this is the interface. Read this as I. And of course, this is the standard one, which is required to supply, what is it, add, reference, release, and so on. And it has 2 private fields. This is where we're going to store the actual function pointed to this anonymous function. And this is the invoke function. I mean, it's sort of standard, you know, when you say, oh, I've created an object and now I'm going to invoke its such and such method. So that makes sense to call it invoke. And this is where we're going to supply this value 6 here. So this is, remember that object on the stack. Well, that was, yeah, sorry, just ignore that because that's going to, and we need to actually create an instance of this class. So yeah, so let's have a look at create. So we're gonna take in a function. This is the anonymous function. And we'll create the object, and we'll populate the the f-func field with actually with a function pointed to this function. And then what we'll do is, well, under the hood, Delphi will call invoke, and it calls it with this value 6, which is fed in here. And remember, f-func points to this. So this is how this is executed, and it returns the result. So when square is encountered, class, don't worry about this name in front of it, but this is standard. If you like, an action record is created, and it's a constructor call which creates an object with a single method invoke with same signature as the anonymous function assigned to square. Invoke is then called with argument 6. Invoke then calls the anonymous function assigned to square, passing it 6. So I think I have a program to demonstrate this. A non-object reference. Yeah, so if you like, under the hood, you create this object with this anonymous function, and you assign it to an object record. I say a non-method because it's under the hood, and then you call the invoke method on this anonymous object with the value 6. So try anonymous method square project. Okie doke. I'll do as said. So anonymous method square project. So we need to yeah, okay. Well, it's not really going to be very exciting because we're not looking under the hood. But so we need to look under the hood, basically. So sorry, I'm just going to check the how long am I going for? But yep. Okay. So let's return to the PowerPoint. So we do from current slide. So we've just done that. Okay, reflective programming. Reflection can be used for observing and modifying program execution at runtime. In Delphi, reflection allows inspection of classes, interfaces, fields, and methods at runtime without knowing the names of the interfaces, fields, methods at compile time. Allows the inspection of classes, interfaces, fields, and methods without knowing the names of the interface. So you would do something like get methods, get fields, get interfaces. But if you do know the interfaces, you can use get method, get interface, etc. It allows instantiation of new objects and invocation of methods, because you're grabbing what's there under the hood in the runtime system and say, oh, make me one of these or make me two of those. This could be this is another way that you could get a Delphi program to interact with a Haskell program. Reflection is a key strategy for metaprogramming. And that's what Richard Pawson's naked functions framework does. It leverages metaprogramming using reflection. So a programming technique in which computer programs have the ability to treat other programs as data. It means that a program can be designed to regenerate, analyze, or transform other programs and even modify itself while running. So going back to the days of assembly language programming. So, and we need to use the RTTI unit. So I'm going to demonstrate reflection here. And we need variables because we need the context. We need a type. We need a create method because we're going to use that create method. And I'm going to display, I've got a display hello message method, and I'll have a test object. So what I'm going to do is I'm going to get the runtime context, interfaces, methods, fields, and I'm going to assign it to RTX. And then, well, so yeah, because I need to create, that's an object. Then I'm going to use this to get the type of something called t-test. So it's a class. So in this case, I'm being specific. Instead of saying get types, well, I don't know the types. I know there's a type called t-test, okay? And I'll treat it as an RTA instant type, and I'll assign it to RTT type. Yeah, there. Okay, so now I know there is a create method on this t-test class. So if I use get methods, I wouldn't need to specify, but because I'm the author of this, I know I've got a create method. So I'm going to get that create method and I'm going to assign it to RTTI create method. And this is an RTTI create, RTTI method type. And then I'm going to create an object, and I'm going to assign it test object. I'm going to use this create method, and I'm going to invoke. So under the hood, this RTTI structure has an invoke, and I'm going to get the class type. That's t-test class. And so if I need to pass any parameters, I could use this. I'm actually going to create this object, and I'm going to say, yeah, okay, make it an object. Okay, so as object, so its type is right, so it could be accepted by this. Okay. Now this is the context. So now I'm also going to get this display hello message method, which I know is there because I actually have defined t-test.create. So, yeah, sorry, there it is. Yep. Okay. Now what I'm going to try, I'm going to try and call this method. I'm going to invoke it on the test object, this object here, which I've created. Okay, and see if it works. So it should run this hello message, and then I'll free the object, basically. Okay, so proceed to demonstrate reflection, I call it, and we'll see what happens. So what is it called? Reflective programming project. So if I come out of this and go into Delphi, and what I'm going to do is no, it's not that one. Reflective programming project. So okay, so it's as described already. So if I run it, the type t-test class is found at runtime by interrogating the runtime type information. A reference to its method create is then obtained and invoked to create an object of this type. A reference to its method display hello message is obtained next, and then this method is invoked to display this message. Okay, press return to close this console window. Okay, So what I haven't shown you is unit1.pass, because unit1.pass contains the class definition t-test class. It also contains the implementation of this procedure, and what I just read out was executed by this display hello message, and all that the create message here does is it runs the inherited one. Okay, so let's return to the slideshow and see what's next. I probably will skip this because I'm a bit short of time. Delphi allows methods and properties to be declared without writing their implementation. So this type of declaration without an implement is called an interface. So if we had a function sum to n defined in this interface isum, we have to provide an implementation for it. An interface can't do anything without an implementing class. The implementing class must declare that it's implementing the interface. So it does this via class definition. Here, this is Delphi supplied, and we're saying we're implementing that. And in a moment, I'll show you the code comes up. This is what it looks like. Okay, and this is the program. So there's an interface unit, there's a class unit, some object reference references isum, because we have to do that to access tsum. It creates the implementation, and then we can run some object reference. So that's Delphi interface, and as I said, the way that Delphi implements anonymous methods under the hood is based on interfaces, because they clear up after themselves. They release the memory they've grabbed on the heap. Okay, so remember, as I said, so I made that mistake. I put t instead of I in front of the reference. I've corrected it here. Okay, so in essence, if we define an anonymous method, it ends up being an interface reference with an invoke method. That's the global unique identifier. You can generate with Control G, whatever it is, it creates a class based on that. It puts the anonymous function pointed to it in the ffunc field. It has an invoke with the same signature as this. It has a constructor, and that's as before. Okay, so yeah, so examining anonymous methods under the hood. So we've got a partial function application here. Basically, when it's running, we want to be able to access the same memory that object created under the hood occupies, and we do that with the keyword absolute. So we've got add6, which is our anonymous method function type. So we've got add8, and I've got two interface variables here, so I can get it the memory where that is implemented and that is implemented. Okay, so we've got an anonymous function here which uses closure. X is captured in the inner scope, so it's carried away when this is returned. I want to report memory leaks on shutdown just in case the interface I know the interface will clear up after itself. So what we're going to do is this f here, we're going to make a specialized function where we supply 6 to x. So what is returned is 6 plus y, and we'll assign it to this variable here, specialized function. I'm going to make an object, a type T object, which is this interface reference as an object. So basically, as I said to you before, I want to go to the same part of the heap where this add6 has been created, and I use my T object to do that. So I want to know the class of TMyObject, and I'll store that in my class. Now, as before, we need an RTTI context because we want to grab what the runtime system looks like, and we want to get access to the class, and then so don't worry about this. This just sets the color that WriteLine writes in. In this exercise, a closure is used to produce a specialized single argument add function. The specialized add function is a pure function. It has no side effects, and for a given argument, the value returned is always the same. Okay, so we're then going to call add6 with argument 8. So remember, add6 is a specialized function. It's a partial function that will add 6 to whatever it's supplied with. In this case 8, so that should be 14, and then I'm going to write it out as a string to the screen. What I'm also going to do is I'm going to write interface info my T object, and also say, well, this is my T object for add6. I need to show you what I've forgotten exactly what how I wrote write interface info for the moment, but I'll come back to it. So we're going to create another specialized function, but this time its closure will capture 8, so it's a partial function that will add 8 to whatever you supply it with. We're going to create a second object, which is why I got the second interface reference, and we're going to call the specialized function add 8. I'm going to add 16 to 8 to create 24. And then I'm going to actually explore the memory that is occupied by this anonymous function. And then I'm going to actually apply the partial specialized function add 6 to 100 to make 106, and then to specialized function 8 to 100 and get 108. So that's it. What I'm also going to do is later on I will interject a new variable 9, and I'll change this to +z, and I think when I run it, do it in this example, we'll have 3 fields that we can actually display, maybe. Okay, so now I need to go and look at this program. So let's go to the program. So let's close this, let's close this, let's close this, and let's go to it's the add, wait a minute, so this one. Okay, so let's do Control V, and it has, this is the way I get different colours, okay, for the WriteLine, to make the written statement stand out a bit more. So everything is there that I've described. By the way, we will see the reference count for the interface, and it will be 2, because we have both the specialized add function referencing the instance and the iInterface variable via the use of absolute. Now remember that a closure uses the interface mechanism. Absolute means variable interface ref should reference the same address as add6. Okay, so let's run it. Let's make it bigger. Let's make it properties. So font, make it 28. So the specialized add function is a pure function. It has no side effects, and for a given argument the value returned is always the same. Core specialized function add 6 with argument result it returned is what? 23. 3. Hang on. Have I made some changes here, which I'm not familiar with? What did I do? Oh, I know, because I've left that in. Sorry. So I need to do this. So I do apologise. So what I need to do is just close that. That surprised me a bit. Okay. So in this exercise, blah, 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 core specialised function add 6 with argument 8, return is 14. The specialised function add 6 is located in an instance of the type. So that's the class name. This instance is located at memory address that. And the instance has 2 fields. Field number 1 has field name X and is data type integer. That's the closure. That's the captured free variable. It has value 6 and its offset in this instance is 12. Field number 2 has the fref count and data type. It has the value 2 and its offset. And that's because we have 2 things referencing this object, as I said. The actual anonymous interface, and we also have the absolute reference that we set up so we can read the information. Okay, so the second one, add 8 to 16 is 24. 2 fields, the captured field in the closure has value 8, and so on. Okay, so that's that. So if we go back to the PowerPoints from the current slide, this is the one on steroids. Okay, I think, is it? No, I'm going to skip this one because we haven't got time. This is the one on steroids. So we've got a class viewer to view the classes. It uses all the RTTI stuff. I think it uses an extended RTTI form show. We're using the generic tproc to reference an anonymous procedure, which Delphi defines as an interface. We need to be able to see the object on the heap, so we need to reference the using absolute the same area. Okay, we've got 3 variables here, which we assign those values. Now we've got this time a procedure reference, and it shows the message. Oh, sorry. The sender class name, the value of X, the address of X, Y, Z, and it also shows the interface reference. So we're going to call procref, sorry, what have I got here? This is within the form show. We're going to load the class interface references object. So this is where, so we're looking at procref, but we're getting into this area here. Now remember, I said that the actual function pointer to says, what have I called the I can't remember now, square whatever. So we're going to look at vmtview.pas. Now this is not original. I got this from an article, and the link is here. So let's have a look under the hood, and let's go to this. So we want to close this one, and we want to go to I know I got a bit confused with this earlier when I was creating this project group. So I want VMT. So let's have a look at this then. So let's do Alt V, and there are a lot of classes. Okay, so I'm going to load that one, that one, that one, and that one. Okay, so this is our form, and then we're going to reveal the published fields, etc. So if we actually have a look at this, this is as described. and I do release the yeah, I do have to release the you know, I got this interface reference so I can see the memory on the heap. For some reason I needed to release it. Okay, so there is a release method. Okay, so I won't look at the rest of the code because it is, as I say, it's a VMT viewer on steroids. So that's my show message, which comes up in the here, show message here. So class name is T class viewer because this is what I'm using to view. X is hello world, address of X is that, Z is this, the interface reference is T class viewer, form shows, and there's this, what you get whenever you're using anonymous methods under the hood. Delphi uses this reference here, this identifier here. So now this RTT viewer on steroids enables me to look at all the RTT fields which have been captured, and so you can see it's got a reference to this anonymous procedure. It's got Z, it's got Y, it's got X, and the sender. Okay, let's get on to Delphi and Cortex Pascal. I'll run the Delphi program first of all. So let's go to here, and I'm going to choose the times table. So 12 times, no, not 12 times table, just the times table. So let's load that up, and it's got a unit. So it's a VCL application, and it uses an anonymous function, which uses closure because X is a free variable and Y is a bound variable, and it multiplies X by Y. So I just did this so it's similar to Cortex Pascal. So what have we got? We have got for var I becomes equal to 1 to 12, to add to the memo box, return a partial function I applied to n. So we'll have a fixed n, like say 6. So it's going to do the 12 the 6 times table. So we call this anonymous function because we want a partial function, a specialized function, and we supply it with I. So first time in, it'll be 1, and the partial function here, x will be 1, and what will be returned is this function here, which is 1 times. The next time it's called, it'll be 2 times. The next time it's called, it'll be 3, all the way up to 12. Now y is this second argument, so it's the 6 times table. So essentially, I create this table by okay, let's have a look. So if I choose 4, we get the 4 times table. So it's using a specialized function. So I'm specializing the function to 10 now. Sorry, no, correction. The way I've done it is 10 is this argument here, but the partial function is continually being respecialized. It's a 1 function, then it's a 2, then it's a 3, then it's 4. This is trivial. I know I could have just said I times n to give the same output. But I wanted a very simple example, and this is the very simple example. So apologies for that. So let's have a look at Cortex Pascal. So sorry, I just need to close this, and I need to open the times table project. Okay, and I want to load QTX times table. So this mirrors the Delphi application, and the code is very it's Object Pascal basically. So there's my partial specialized function. There's my handle number. So here's my return a partial function I, and that just creates the window and so on. So if I build this, that creates the index.html and the index.js, and then I execute this. This is in a local browser, but I could open it in any browser, and so it's exactly the same. So I've just taken the what I wrote in Delphi and put it into. So let's open it in a browser. So it's the Edge browser, so I could basically load it up to a website if I needed to. Exploiting parallelism using an anonymous procedure. This is how to calculate primes. One way to calculate primes. So let's say we have an upper integer which is 10 million. I think is that. Yeah, 10 million. So we'll use a stopwatch to get fine timing. And what I'm going to do is just calculate. Well, I'm going to go through all the numbers between 2 and this upper integer is 10 million and test if they're prime. And if they are prime, I'm going to add to the total, which is initialized to 0. And then I'm going to write stopwatch. Non-parallel loop, time in milliseconds, blah blah blah, counts the number I've given a value using parallel. No. So right, what I'm then going to do is do it using parallelism. So I'm going to use the t-parallel primitive, and I'm going to pass in this anonymous function, and there's my range. So start the watch, stop the watch, and then I'm going to write out how long it takes, basically. So we're going to have multiple threads, but I do need to be careful about, because we have multiple threads, we've got to stop them all trying to update total at the same time, and we'd have a lost update problem. So we interlock total until we've incremented it and then release it. So each thread tests a different part of the range, 2 to 10 million, and we avoid the lost update problem as I've just described. Okay, in order to give exclusive access when updating. So we need now to demonstrate this. So if I close this, and if I go to parallel versus non-parallel primes, so do Control V. Right, so here's what I've described already. So if I run it, so twiddle one's thumbs, because the single threaded execution calculation is quite slow. So it takes 664 seconds, because it's in milliseconds, and that's the number of primes that have been found. But for the parallel one, it's only taken 1 second. So 1476 milliseconds. So if that doesn't convince you, then I'll eat my hat. Well, I haven't got a hat, thank goodness. So okay, so onwards and upwards. Next one. Current slide. So we've done that. Oh, it simplifies parallel communication since two purely functional parts of the evaluation never interact, and a function always returns the same output given the same result. So as I said, we divide up the range 2 to 10 million and allow a thread to execute it for each. Yeah. So let's have a look at the use of anonymous method in callback. So AJ, which stands for asynchronous JavaScript, and XML is a web development technique that allows web applications to send and receive data from a service asynchronously without interfering with the display and behavior of the existing page. This means that it is possible to update parts of a web page without reloading the whole web page, enhancing the user experience by making the web application into more interactive and responsive. Okay, so if you're in any doubt what AJ was, hopefully you are enlightened by now. So we're going to create two anonymous procedures. One's an AJAX callback, one's a link callbacks. So we're going to act on the response when it comes in, and we're also going to act on a link when we can get it from the response. So we've got an AJAX call which uses an anonymous function here. We've got an extract links which uses this anonymous reference, anonymous method here. Okay, so we have a t-ajax thread which is used. Which is used to set up the HTTP connection, specifying the URL and the callback function. And when we create this thread, it will start executing. So we need to create it first here, etc. Okay, so what we're going to do, we're going to make the AJAX call, and we're going to specify the URL, and we're going to supply a callback. So when we get the response, we're going to access that response and assign it to a memo box. And we're also going to insert the URL that we specified. Now, if we clicking on a link that is present in this response, then we're going to make another AJAX call, and we have another anonymous function here, and we're going to extract the links from the response, and we're going to add them to the memo box. We're going to show the HTML. Okay, so so the AJAX call is constructed this way. So we create a thread, we specify the URL, and we specify a callback function. Okay, and I'll demonstrate this. Oh dear, sorry. So if we click on this, we actually go to blog.marcocanto, because I extracted this from Delphi's Object Pascal book, but it didn't work because he's changed things on his, because he's now got an HTTPS site, and the images are a different format, so I had to adapt it basically. But we've got back the base of the web page, and then this will find the links in the web page. Oh, sorry, I'm not running it yet. And then finally we'll get the images. Okay, so let's go to this. We'll close this, and we want to go to the So we'll do that. Okay, so we've got that, and we've got that. So this is an adaptation marker counters program from Object Pascal Handbook Master, Chapter 15. Marcus program doesn't work for 3 reasons. It is set up for blah blah blah. Marcus blog is now that. It uses IDH HTTP, which doesn't work as written for HTTPS because it requires OpenSSL DLL. Okay. It uses image1.picture graphic load from stream A to load the first graphic from Marcus Bless site when this is a PNG graphic now. So we need to do that. Also need VLC imaging as a main unit. The demo source code copy is copyrighted markup, but can be used freely. Okay, so I have emailed Marco and sent him a copy of this, and I've spoken to him and so on. I think he will eventually get around to changing the book. So that's everything that I've described already, well, except the detail of extracting the links and the images and so on. But really, what I'm focusing on is the use of callback in an asynchronous call, because it's an AJAX call. So that's as described, basically. So if I run this, okay, read from HTML, get links in HTML, get images, and there you are. So that's that. That's Cortex Pascal. This is another one that I created in Delphi, and then it's just mapped into Cortex Pascal. So if I go to this, you notice the delay there, and that's because I created a JSON file with 23,000 entries. These are all the computable starting patterns. I use Delphi to obtain these. And because if I didn't delay setting up this user interface until all 23 entries had been downloaded, it would have gone wrong. So I have a delay of about 200 milliseconds built in, and when that 200 milliseconds times out, it calls an anonymous method. So that's the callback to finish off setting up the interface, basically. So basically, this is the inheritance diagram for the Cortex solution. This is what I wrote in FMX, Delphi FMX, a long time ago. It needs change. The tractable needs changed into computable, and I need to add the JSON library. And you see, this is so similar. It's so easy to map across, basically. I basically think I'm not going to be able to get onto this last one or to the higher order functions, but then they are available from the site. They are out there also on YouTube, and I did do them in a previous webinar for Embarcadero, and they are available from Embarcadero. So I am going to stop at that point, because otherwise I'm